Okay, it's 9 o'clock East Coast in the United States, 3 p.m. in Germany. So, Gesine, let's start. Hello, good morning, good afternoon, and good evening. This is Paul Liu from North Carolina State University. Welcome you again to this World River and Delta System Source to Sink webinar series. Today is our great honor to invite Professor Gesine Mollenhauer from Alfred Wegener Institute for Polar and Marine Research. Come here talk about Lena River, particularly organic matter transport through this river and its delta to the Laptev Sea. So it's a very interesting talk, and we have been talking about the tropical river and the delta. For example, Amazon, the Mekong, the Irrawaddy, Ganges, but only a few talks so far talk about high latitude river and the delta system. Particularly, this is the first one talk about specifically the Russia River and the Delta system is our long reach talk. And so we're so glad. Before I introduce Gesine, so as always, I know today there's some new audience coming here. And our previous talk, this is 52 talk in this webinar series, number 52 in this year. Last year, we have 35 talk. All those talk has already been archived on our YouTube channel. So you're welcome to check all previous talk. Like today's talk is also live stream on the YouTube, as you can see here. So it's tinyurl.com/S2S talks. So you can subscribe this YouTube channel. At the same time, if you are active on social media, particularly on Twitter, so you're welcome to follow our Source to Sink Twitter things. So as you can see, you will receive the new announcement for the coming talks, like today's talk given by Gesine is over there. And our next Wednesday, Tony from UNC Chapel Hill, he will come here talk about North America, particularly coastal sedimentation in this century. And he will see how the sediment flux changed in the last century in the North America, United States, focused on particularly East and the West Coast. Okay. Gesine Mollenhauer is the senior scientist at Alfred Wegener Institute for the Polar and Marine Research. As you can see, he was there since 2011. And before that, he worked on Netherlands postdoc and also a postdoc at Woods Hole 2003 and 2004. Very interesting. I'm not sure when you arrived at Woods Hole. I've been there from March to September, only 6 months. I'm not sure we have an overlap or not.
Oh, I was there all of 2003. I actually arrived late.
Maybe we definitely came across on the campus. I only have very short postdoc over there, 6 months. And then, as you can see, she graduated from University of Bremen and also get their, I guess, bachelor and doctorate degree over there. Her research is kind of combined use organic geochemical technology and biomarker and also radiocarbon to trace the transport and the carbon cycling process across the land-ocean interface. And she has have very broad research area all the way from not only the high latitude, but also tropical, not only the Europe, but Asia, America. So we are very great honor to get her today, come here to give us a talk. So Gesine, please go ahead, share your screen.
Well, thank you very much for this introduction. I'm now trying to share my screen. Can you see my presentation in presentation mode?
Yes, it's good.
All right. Thank you very much. And thanks for inviting me. Well, you did the introduction to myself, so I'm going to introduce you to my group, who's now not looking at anybody here. So that's a wonderful shot that we took during our group outing a few months ago, and it was just before my camera died. So nobody's looking at me, but you see it's a happy crowd, and they are not afraid of northern German weather. They're even wearing shorts, so they're all polar researchers and know how to deal with cold weather. What we are interested in is mainly two areas of research. And one is, what is the impact of the cryosphere on atmospheric greenhouse gas levels? And in this context, we're investigating which type of organic matter is mobilized when climate warms. That's something that I'm going to talk about today, or try to summarize what I think I know about this process today. And there's a typo too. Which processes lead to remobilization, and what is the fate of this organic matter? Is it burial, or is it decomposition, or to which extent is it buried or decomposed? What impact does this process have on atmospheric CO2 levels? And we're using the geological past, in particular the last deglaciation, as an analog for the present warming. And we're also interested in looking at the signals themselves and try to understand how paleo-environmental signals are altered during transport to and in the ocean. And we're using biomarker signatures. And we also look at how isotopic characteristics are preserved or even changed during transport and after deposition. And the toys that we're using for that are mainly organic geochemical techniques, nothing particularly fancy biomarker studies. And we're lucky that we can combine that with the use of radiocarbon, since we have access to a small scale accelerator mass spectrometer. So one of the areas that we're particularly interested in is the Arctic. And why is that? Probably all of you have seen this picture that illustrates the change in temperature over a mean across the past 140 years, basically. And that's plotted on a latitude scale. So very far up is the temperature in the high northern latitudes, and very far down is the temperature in the high southern latitudes. And the Arctic, that's this region here. You can see that over time it has become warmer and warmer and warmer. So that's what's known as Arctic amplification of the temperature increase, because it is warming more rapidly than all the rest of the globe. And this has very important consequences, because one special thing about the Arctic is that it hosts much of the land area, and this land area is to about 25% covered by permafrost. Here on the left, you see the distribution of permafrost shaded in blue, with dark blue marking the continuous permafrost area. That's the area where the entire ground remains frozen over at least 2 consecutive years. And then we have discontinuous permafrost, where there are unfrozen patches between the frozen areas, and isolated permafrost patches that are largely remnants of the last glacier, when the permafrost area was much larger. And what you see also is are the catchments of a couple of very big rivers, most of them draining into the Arctic, one draining into the Bering Sea, the Yukon. And this makes the Arctic Ocean a very special place, because it receives so much river runoff compared to most of the other regions in the world. And an isolated ocean like the Arctic receiving so much river runoff makes it a really special region in terms of freshwater budget, and also in terms of terrestrial organic matter input, because here in the right, you see the soil organic carbon content, which is very high in some of those permafrost regions. And this is a very simple explanation. The soil organic matter does not decompose when it's frozen. That's much what you do when you put a pizza in your freezer. It's not decomposed. And so in these regions, soil organic matter can accumulate. If you look at this in another way, you can see how much organic matter is really stored in those soils. So these are just bubbles that represent the size of important carbon reservoirs. For instance, the atmosphere of today, which is very strongly anthropogenically impacted and contains about 880 gigatons of carbon. The vegetation, 500 roughly. The global soils, about 3,300, and approximately half of that is within the permafrost region. And most of that is in the frozen ground of the permafrost. And there's even potentially more in deep permafrost carbon, which is not well characterized and not well quantified. And compared to the fossil fuel reserves that we think we can find on Earth today, this is a substantial amount. It's about the same size of carbon reservoir in the frozen ground as in the fossil fuel reserves. And if we think about how much damage you can do by liberating fossil fuels to the atmosphere in the form of CO2, we can imagine that unfreezing this frozen ground and mobilizing carbon there is a potential threat to the climate as we know it today. And this permafrost is really thawing. So we know the Arctic is warming, and this is how it looks in the summer when a permafrost deposit is subjected to above freezing temperatures on a nice sunny day. You can see the organic matter that's contained in it falling down, and there's a lot of water involved, and this water is draining into the large river systems that are present in these regions. So it is an active process, and it's a process that's accelerated by Arctic amplification. Okay, so this is another representation of the Arctic Ocean, and you see marked here again several of those rivers. Now it's a more complete map, including also some of the smaller rivers, but you may recognize some of the ones that had been marked before: the Lena, the Yenisei, the Ob, and the Mackenzie. And these Arctic rivers have a cumulative carbon discharge on the order of 25 teragrams of carbon in the dissolved organic carbon form, and about 5 teragrams of carbon as particulate organic carbon annually. So that's quite a bit that is discharged into the ocean. And at the same time, we know that the discharge of those rivers is increasing over the past decades. There are variable or variations in the discharge of the rivers, but overall, there are pretty pronounced trends of river discharge increase over the past few decades. Here, overall, we see about a 30% increase between 1980 and 2009. And another aspect that is evident in all of these rivers is that the spring freshet, so that's the flood that occurs when snow melts and when ice breaks up, occurs earlier and earlier. This is the Lena River, which is located here in eastern Siberia. And this is the river that I will focus on most during this talk, because this is a river system that is studied by our institute in greater detail, I should say. Those Arctic rivers have a pretty large carbon yield, the catchments of these rivers, and there is a lot of work done in the framework of the so-called Great Arctic Great Rivers Observatory. This is a consortium of several colleagues, mainly from the US, who got together to set up a continuous sampling program of those large rivers, whose drainage areas are marked here in the bottom. And these data are freely available, and there are very interesting publications about these data. One of them is by McClelland et al., was published 5 years ago, and it summarizes, among other aspects, the carbon yield per area and year of those river basins. And you see one very pronounced characteristics is that all of them yield more DOC, dissolved organic carbon, than POC, and that the amounts are really large. And here the Lena is one of the very big players. This is what the landscape in parts of the Lena River drainage area looks like. You see that it's very wet. This is the so-called Polygonal Tundra, which consists of polygons here in the front, for instance, which are surrounded by rims. And underneath these rims, there are ice wedges located, and they elevate the ground around it. And this is a very productive and very swampy area. And you can imagine that through the unfrozen part of that at the surface, which is unfrozen during the summer, there's a lot of water circulating, and this water is also draining into the river. So that's already a rich source of dissolved organic matter. Much of the deposits in the Lena Delta are composed of Holocene peats. This is a picture of what this looks like, a very muddy thing. And you can see that the cliffs or the bluffs are elevated over the river level, and they're very easy to erode as well when they fall into the river. They are very, very rich in organic matter. Here's an example that is taken from a publication discussing Canadian peats, but this is not much different than in other permafrost areas that have these Holocene peats. So very organic rich, and their average age is somewhere in the Holocene, in the mid-Holocene. So you can find younger peats and older peats, and on average, this Holocene organic matter is maybe about 7,000 years, 7,000 radiocarbon years old. You also find these kinds of deposits in the catchment of the Lena, and these are very peculiar formations, I should say, that consist of frozen water, so watery ice here, that you see here in gray, that contains these large, very organic, rich, silty soils or deposits in it. And when you subject this to an above freezing temperature, this water ice will melt and the water will trickle down, and the soil parts in between, they will fall down like these big blobs that you see on the bottom here. And this is a very effective way of eroding a coast. The coasts that are composed of this kind of deposits erode at rates of several meters per year, up to 20 meters per year. So you can imagine that a lot of organic matter is really transported into the adjacent rivers by this erosive process. Oh, there we go. And this is how it looks when it's about to fall into the river. And these materials, these deposits are called Yedoma, so ice complex deposits, Yedoma deposits, and they also are relatively organic rich with a fairly large spread going up to over 20%, but the mean is here in the air, around 2.5% organic matter. And these materials are really old. This is a plot that's taken from a publication by my colleague Jens Strauss at RWE Potsdam, and he compiled all the data that are available for these Yedoma deposits in terms of their radiocarbon age and their latitudinal distribution. And you see that most of them are really from the Pleistocene. So from, maybe 10,000 years down to over 50,000 years beyond the range of radiocarbon dating. So we're looking at the relict of the Pleistocene. And after that, after the Pleistocene, not much of this material has formed anymore. So it's a facies of the Pleistocene, of the time when the mammoths were walking in this area and grazing. And they played a role in the formation of this deposit. This map shows a distribution of where these relicts are found, and they're marked in blue, overlain over the continuous permafrost map of eastern Siberia. And here you see the Lena River, which is draining a catchment that contains still quite a bit of this relict Pleistocene material. And it also has this very large delta, which is the largest delta in the Arctic and plays an important role in modulating the material that's discharged through this large catchment into the Laptev Sea, which is the ocean area, shallow, very shallow ocean area here, which also plays a very important role in the formation of sea ice, which travels then across the Arctic Ocean, across the North Pole into the North Atlantic. So that's the cradle, basically, of the Atlantic, of the Arctic sea ice. In the Lena Delta, there is an island that's called Samoylov. And this Samoylov Island is very well studied, mainly because it hosts a research station that is operated by our colleagues from the Russian Academy of Sciences and co-operated by AVI. It is operated year-round, and scientists that cooperate with the Russian Academy of Science and AVI can go there to do all sorts of permafrost research, including vegetation studies or geomorphology. A lot of gas measurements are carried out. And we also established a monitoring system of the river water characteristics here in the island of Samoylov. Here's a more detailed map of how it looks like. So you have all of these very small islands and the channels of the river that are fairly wide and also very shallow are surrounding it. Also marked on this map is the location Kusur, which is a gauging station, a river gauging station. And then we have marked the location Shigansk. And Shigansk is actually the place where the Arctic Road, the Arctic Great Rivers Observatory, is sampling the river and collecting materials. So it's quite a ways from the actual point of discharge of the Lena. It's about 900 kilometers away from the delta, and it's nonetheless taken as the representatives of the discharged, or the material discharged by the Lena River. This is what this research station looks like in winter. You see it looks a bit of like a UFO. And that's another satellite image of the Lena Delta, where you see all the different channels that are widening up here. And these channels to the east are really the ones that count, because they discharge collectively about 90% of the water that's running through the delta. And there are many different types of formation also present in the Lena Delta. You see in lighter green here, for instance, and here, these are islands that are composed of this Pleistocene relict deposit, whereas those areas here that look brownish green are mainly Holocene peats. And then there's a third formation here, which is not mentioned that often, not studied that often. It's very difficult to access. This is the so-called second terrace of the Lena Delta, which formed in the intermediate times between the Pleistocene and the Holocene. And I'm not really going to talk about this today. So I mentioned that at the island of Samoylov, our colleagues in AVI Potsdam are trying to establish a monitoring spot that should look at the content of DOC and the optical characteristics of this dissolved organic matter. And here what you see on the top is a graph of the discharge of water in a dashed black line. It's plotted on a logarithmic scale, and you see that in early June or late May, there's a very rapid increase of discharge. It goes up very, very high, and then it falls down again. So this is the spring freshet, this period here, late June, late May until mid-June typically. And then there's the open water period over the summer. The discharge goes down later in the fall, and then it reaches base flow levels for the winter when the Lena is frozen, covered by ice. And on the right axis, the DOC content is plotted in purple here. And you see that the content also goes up dramatically, simultaneously, basically, with the peak in discharge. And so do some of the optical characteristics. There's an inverse relationship here with the absorption in a certain wavelength band. That is a typical or a way of categorizing and characterizing the DOC. But the main message is the most of the DOC is really discharged during the time of the highest discharge peak. So the highest concentration coupled with the highest rate of discharge into the Laptev Sea. In contrast, the POC, the particulate organic matter, is, well, it's not concentrated at this high levels as the DOC. And here are some data compiled from the Arctic Row database referring to this site again. This is Shigansk, the station where the Lena River is sampled in the framework of this large consortium. And you see also that during June, the time of the freshet, of the ice breakup, typically you see the highest concentration of POC and also of PON. They go down throughout the summer and reach base flow levels in when the river freezes up again, but there's quite a bit of scatter here. We also try to sample POC from across the freshet, the spring freshet. This is a picture of my colleague Antje Oldenburg trying to sample the river from the island of Somolov, and you can already see there are large ice flows that are floating on the Lena, and it has a very high water level, and it's quite dangerous to go out there into the river. So it's very, very difficult to sample. And it's particularly dangerous to go out into the main channels. But this is a way how we can sample it by accessing it really with rubber boots and wading into it as far out as we can. And this is what we get when we do this. So this graph here shows the POC content across the spring freshet in the year 2014. So it's in another unit, but it is equivalent sort of to this. You have a large scatter, but you have the highest values really accompanying the freshet as well. The questions that we can ask when we look at the discharge of DOC and POC from the Lena is, what are the sources of this dissolved and particulate organic matter? I have hinted at the fact that the water flowing through the unfrozen portion of the permafrost deposits is a likely candidate for the source of DOC. Also, I've shown you the pictures of the eroding coasts that certainly contribute quite a bit to the particulate organic matter. But the question is, can we really prove this and see this? The other questions that I'd like to discuss during this talk is, how is this organic matter altered during transport? Is there anything going on with it once it's in the water? And what is its fate? How is it discharged into the Arctic Ocean? Does it survive there? And how is it deposited there? And I'm going to try to run through these aspects during this talk. So let's start with what is known for the samples that have been taken at Shigansk, at this station that's used for the Arctic GROW project, the Great Rivers Observatory. And here's their signature representation of the watersheds. I have put blue boxes around the data that are relevant for the Lena. And here we see data for DOC in yellow and for POC in blue. That's the first distinction. We also have radiocarbon values and C13 values. And the data are also distinguished by season. So there's a spring box, a summer and fall box, and a winter box. And this is really reasonable, as I showed you, that the levels of discharge are very different between those time periods. So the first thing that we see, and that is true for all the Arctic rivers, is that the DOC has a radiocarbon signature that is similar to the atmosphere of today. There is a seasonal variability with the youngest material being discharged in the spring, and there is a bit of a decrease in the radiocarbon content towards the base flow in the winter. And the POC, in contrast, is substantially older. So it's at least 2,000–3,000 years. On average, there is a larger scatter, and there is also some seasonal variability. And if you like, you can see a trend from the westernmost river of Siberia to the easternmost of those that are considered in this Great Rivers Observatory, with younger material coming from the out of the Ob and oldest material coming out of the Kolyma. There's also a similar pattern observed in the DOC, but nonetheless, all the C13 signatures indicate that most of the organic matter or the organic carbon that is found in those rivers has a terrestrial origin. However, one thing that we see here is that in the particles, there's a trend with season, and the summer and winter data have a tendency to be very depleted, much more depleted than what you would expect for terrestrial organic matter. These data are compared in the publication by Birgit Wild and others to data that are available for potential carbon sources that might supply these materials for terrestrial production, so modern plant material, for the active layer, which is the seasonally thawed part of the permafrost deposits, so this part through which water can circulate in the summer. For the Holocene deposits, and I told you before, they're on average about 7,000 years old, and for the Pleistocene deposits. Not much difference exists in the C13 sources, but there is quite a bit of a difference in the radiocarbon between those materials. And this compilation has then been used to make estimates of how much each of the carbon pools contribute to the materials that are discharged. And it's distinguished into or separated into recent carbon pools and old carbon pools here. PP, that's what they use. I forgot what this is meant to say, but PP means it's Pleistocene, pre-age, something like that. And what they found here for the total export, the lighter colors are always the old stuff, and the darker colors are the younger stuff. So most of what is exported is really young DOC, and there's quite a bit of young POC as well. Young POC as well, and then there is old DOC and POC that makes up about maybe 15% of the total export. This graph on the right here also shows another output of this model. And this is distinct again into POC of the different seasons in blue and DOC of the different seasons in yellow colors. And so this is the total contribution of each of those discharge time periods. And this is the material from recent sources and the material from fossil sources or older sources. And there you see that most of the old material is contained in the POC. So disproportionately much of the old material is exported as particles and not as dissolved organic matter. Remember that there's a factor of 10 difference in the discharge of DOC versus POC. And here it's about 40% of the old stuff that's contained in the particulate fraction. So these were the data that were derived from the materials collected at Gdansk, and this is now a compilation of these types of data for POC in the delta. And it's plotted here for different times of sampling from August 2009, summer 2010, and then late May, so during the spring freshet in 2011, and also into late June, early July in 2011. So again, a summer situation. And you see that one thing that's evident, there is quite a bit of a difference between the different locations. So you have very old materials here that are marked in blue and younger materials that are marked in yellow, and then some greenish stuff in between. Here in the next year, there's more of the in-between material. There's a bit of old stuff, not so much young stuff. And here in the spring, we have the oldest materials. Summer has the youngest materials overall. So this suggests that there is no uniform POC that's being discharged, but it's very strongly dependent on where you sample. When we compare the data that we have collected for the Lena Delta, which are the ones that are plotted here in the colorful symbols, so the blue dots for the DOC and the brown boxes for the POC, and compare that with what has been sampled at Gigansk, at first sight, it looks like there is quite a bit of agreement. So we are in a similar range of radiocarbon values, so young DOC and older POC, but there seems to be more scatter here in the POC. These are now the samples that we collected in 2014, including the spring. Another way of looking at the data that we collected for POC is plotting them onto a C13 versus C14 space. And I will walk you through this, what we can find here. So the colorful symbols in blue are the samples that we collected in summer. And that's this tan color also falls sort of into this category, but it's slightly earlier. The red dot is a sample we collected in late May during the freshet. And the gray symbols are data that come from the literature and refer to samples that have been collected off the Lena Delta in the Marina realm. Those gray symbols are data that have been obtained for suspended particles in the marine setting next to the delta. Okay, so we see that there is a distinction in the spring material and the summer material. And the spring material is also similar to what has been found for the first terrace soils. These are the green and brown symbols. So these are the Holocene deposits in the delta. So what we find in the particulate suspended load of the river in spring is similar to what is found in the adjacent deposits. Whereas in the summer, there's a deviation to more depleted C13 values. This is now the same plot, but also but only for data that have been collected in the year 2014. And again, in spring, these are the dark green symbols here. We have less C13 depleted values, and in summer, we tend to have more C13 depleted values and at the same time, younger materials. The gray symbols now are averages found for materials collected at Gigansk. And there we also see that the spring values tend to have the least depleted C13 values, and the winter and summer ones tend to be more C13 depleted. The C14 distinction between them is not quite as pronounced. We have more data than this. We collected more POC in the delta in August 2019, and it is very similar to all the other summer data. And we collected POM in the delta in the winter 2019. So in April, just before it thaws and there's ice breakup. And you see that these are less C13 depleted, but at the same time, they're the youngest, and there's even a data point that falls outside of our range, which is very, very C13 depleted. So it seems like there is quite a bit of a difference in source between the POM between the spring and the summer. And in the summer and winter, our interpretation of the C13 signal is that this includes material from aquatic production, because there is no terrestrial source that is so C13 depleted. Instead, if you recycle organic matter into DIC in the river, and this is then reused by aquatic production, a very depleted C13 signature can be explained. The spring POM is distinctly different. So this is Samoilov Island in the summer, and you see the large or the high bluffs here, that they're about 10 meters high. This is the old research station sitting on top of that. And if you look at the same locations in the spring, you see a picture like that. So the water level is much higher. This is again the old station here sitting on top of the bluff. The water level is almost to the top of this island, and you see these big ice flows that jam into the coast. And this is a very strong erosive power that creates a lot of coastal retreat each year. So it is very likely that the spring material that we find in the river suspended is very strongly impacted by erosion by ice. So it carries a lot of locally eroded materials, and the ice erosion is a very effective way of eroding material from the delta. I showed you some data from this transect that we sampled in August 2019 and also in April 2019. And we also collected some samples along the river up all the way to Yakutsk, or well, really all the way down from Yakutsk to the station. And we're crossing the sampling site of the Great Arctic Rivers Network, and we're also crossing the river gauging location here in Kusur. And the data that we obtained here again in C14 and C13 space are plotted here. This is the transect from Yakutsk to the delta, and these are the delta samples. Note, they have been collected in August. They have been collected slightly earlier in July, traveling down the river right behind the peak of the discharge wave. And these brown symbols here are data for summer from the Arctic Great Rivers Observatory Network. And one thing that is evident is that we have a big difference, or we see a big difference in the POC C14 here at Shigansk. And this is also true for C13, where all of our June C13 values have a very nice terrestrial signature, and then the deviation from the terrestrial signature towards more depleted values, which we could explain by aquatic production, is seen here, and it's also seen in the delta values here. Some of the difference that we observe might be explained by the fact that our values refer to surface samples in most of the cases. We have a bit of deep water samples included here at Storp, but all the earlier data that I showed you were all sampled, obtained for samples collected at the surface. Whereas the sampling at Shigansk is a depth integrated sampling. Nonetheless, the C13 deviation here is not explained by this, because if it's aquatic production, one would expect this to happen mostly at the surface and not so much in the deeper parts. So we're still working on this. You see, this is a manuscript in preparation by one of the PhD students, and we'll hope that we'll come up with a good explanation for our observations soon. So let's move on to DOC. This plot you've seen before, but now it's turned by 90 degrees. You've seen the discharge record for the Lena for 2014, and you've seen the POC values here plotted in green all over the place. And on a different scale, a factor of 10 higher, you see the DOC values. And again, we have a very nice maximum that goes along with this discharge maximum. These are the C13 values with more or less terrestrial values here for the spring, and then the deviation towards more depleted values in the summer. This is radiocarbon that has older values here in the spring and younger values in the summer. For POC and for DOC, there's a bit of a decrease with increasing thaw depth likely. Oh, sorry, I didn't want that. I want to go back. Okay. And then maybe it goes up again once the soil starts to freeze again from the bottom. And not much going on in C13 of the DOC. But we can look in more detail. We looked at the composition of DOM using FDICR-MS, so very high resolution mass spectrometry. And we plot the results. This is only a snapshot of the results. I cannot show you all of what we had, but this is a comparison of the peaks that we obtain for the sample from June, a water sample from June. These are the black dots. And plotted on top of that are samples from August 14th. So a spring freshet versus summer situation. And this is a so-called Fangrivlin diagram that has a dot for each compound that is found, symbolizing its O to C content, so oxygen to carbon content, versus its H to C content, hydrogen to carbon content. And this is a measure or explains, oh no, sorry, these parameters are different for different types of compounds. So in a simplified way, one could say we would expect compounds like lignin, so the very high polymer, high molecular polymer that constitutes much of the rigidifying agents in land plants. These compounds should be situated somewhere here. Tannins are derived from peat bogs and similar settings. They would be found here. Carbohydrates here in the upper right. And as we move down in oxygen content, we move towards proteins and lipids. And when we go back one step, we see that in the area here, up where the lipids and the proteins reside, we see more of this material being present in the sample for the spring rather than for the summer sample. On the right, we now plotted the correlation coefficient of each of those compounds versus the DOCH. And the color coding indicates that a compound is more abundant when the radiocarbon is high and that the C14 is lower, this should say. So the H is higher when it's red here. I apologize for this error, it's lower. And the C14 is higher. When the C14 is higher, these bluish compounds are more abundant. So when the sample is younger, the bluish compounds are more abundant. This indicates that aging is accompanied with loss of compounds like proteins and lipids. So they might be very rapidly decomposed. We have more molecular characteristics of our particulate and dissolved organic matter for the year 2014. The green symbols are always for POC, the blue ones are for DOC. And what we see here is, for instance, the CPI, the carbon preference index of alkanes, which indicates more degraded material when this goes down. And our data here have a slight tendency towards more degraded values in the summer. This cryptic acronym here is a modified aquatic to terrestrial ratio of long chain N alkanes. And this goes up as we move through the season, if you are willing to consider this an outlier. So we have a tendency of more aquatic contributions as we move to summer, which is in agreement with our isotopic studies. The delta D of a long chain N-alkane also changes over the season. We have less depleted values in the summer, which might just be a small indication for an increased contribution of material or relative contribution of material further down in the catchment. I'm not going to go into detail with this, but this is one way of interpreting it, maybe others. And we have a parameter derived from our DOC compositional data that refers to the state of degradation. And as this IDEC index goes up, we have more degraded DOC. So this is again an indication that with warming into the summer, we see more degraded organic matter in our river. This has been suggested by previous work, for instance, by work that Paul Mann conducted for the Kolyma River. That's another one of those great Arctic rivers that receives a lot of runoff from Pleistocene deposits. So these Jedoma thaw streams And Paul has sampled those streams and has radiocarbon dated the DOC in the thaw stream, in the erosive streams, in the streams, minor tributaries, major tributaries, and the main stem of the Colima. And what he found is that the old stuff that he would expect in the Pleistocene deposits disappears very rapidly. There is no sign of this old material left once the water reaches the mainstream. And Bob Spencer has incubated this material and has performed FTIC-RMS measurements on these DOC samples. And what he found after 28 days of incubation is that, again, in this area where we see lignin and tannin, a relative increase is observed, whereas in the area where we see proteins and lipids, we have a almost complete loss of these compounds during the course of the incubation. So this is supporting our results, but from a very different experimental approach. Whenever the organic matter dissolved in the stream is degraded, we're losing this portion of the Fangrivlin diagram, and we're enriching this portion of the Fangrivlin diagram. We also performed or looked at how radiocarbon ages evolve as water travels through a drainage system here on the island of Coronach. And Coronach is located in the Lena Delta, and it consists of a elevated Yedoma unit here, termed the third delta unit. And this delta unit with Yedoma has these thermokarst lakes. One is called Lucky Lake, the other one is called Oval Lake, and they're connected by these streams. And then those drainage, that this water drains across a bluff down to a Holocene non-Yedoma unit of the delta, and then ultimately reaches the main stem of the river. This drainage system has been sampled in several years, 2013 to 2017, and in 2016 and 17, we also collected samples for radiocarbon dating of DOC. And what we found is that the radiocarbon values in this system change as we travel along the flow path. The oldest materials we find in this steep thermokarst lake, this is here, and as we cross down to the first delta unit, this old material seems to disappear or become less important. There are several processes that could explain this. One of them is rapid degradation and outgassing of labile Yedoma-derived organic matter, but at the same time, we also see a change in concentration along this flow path and a change in the stable isotope values of the water. And if we perform mass balance estimates of whether or not we can explain our signal with degassing or with dilution, that's another option, that we have input from the first delta unit to our stream, we come up with inconclusive results. So both processes could potentially explain our results. It's not only that this labile old DOC is degassing, but we might also just dilute the signal with younger DOC. Finally, before we end, I would like to talk a little bit about the fate of this organic matter that is discharged from the Lena Delta. And here's the satellite image where you see that there is a cloud of particles suspended in the ocean off the Lena Delta. So this very rich load of particles that's discharged, that has to go somewhere. And we sampled the shallow lab depth sea along several transects. They're probably difficult to see here, but all of these stars indicate a sampling location. And for all of them, we also obtained C13 and C14 values. So I'm going to show you again the C13 versus C14 plot that we had before for the PUM. These are the data to remember for 2014. This is the spring material. This is the summer material. And when we now plot our surface sediments, as well as marine surface sediments collected by colleagues in the past, we see that they are somewhere closer to the spring values, maybe even more depleted than them, but nowhere near the summer values. There is no agreement between summer discharge material and spring discharge material. And if we compare that with Holocene first terrace materials, we are again in agreement with spring values and with sediments, even though they're more aged than the POM that we see in the spring. This suggests that all of this aquatic produced material, even if it's a lot, it never makes it down into the sediment. Whatever we see here is dominated by the materials that are eroded in the spring. Lastly, we also looked slightly back in time and looked at two short cores that were recovered during the sampling campaign. These are the two core locations. They cover about 1 century back in time, and they were taken off the main branches of the Lena River Delta. And for each of these cores, we performed radiocarbon dating of TOC. These are the gray symbols here. We also obtained compound-specific radiocarbon dates of terrestrial biomarkers and of aquatic biomarkers that represent a mixed signal between terrestrial and aquatic sources. And what we see is that most of the organic matter is probably terrestrial, and there is no big change with depth in the age of either the terrestrial compounds or the bulk organic matter. In particular, the terrestrial compounds, which are unaffected by addition from marine sources, remain very constant over time. So even though we see an increase in discharge from the Lena, we don't see an increase in old organic matter being mobilized, which is the fear in the thawing permafrost regions. The content of the shorter chain fatty acids, which is the aquatic biomarker, goes very strongly up here towards the top. But you can also look at this as a signal of very rapid degradation of fresh matter that is added at the top and then disappears in the sediment as it's consumed by bacteria very rapidly. And this is also consistent with a C13 signature, which contains a more marine signal here at the top, which goes down very rapidly. So overall, what did we find regarding the three questions that I introduced in the beginning? What are the sources of dissolved and particulate organic matter? The DOM carries a signature that suggests that it's mainly originating from near surface thawed deposits, but it may contain H components in thermokarst lakes and streams, which may disappear very rapidly. Particulate sources vary with location and season. There is aquatic production in summer, which provides a substantial portion of this. But particulate organic matter that's transported to and buried in lab-depth sea sediment is dominated by material that's likely eroded during the spring freshet. How is it altered during the transport? There is apparently a rapid alteration and loss of ancient DOM, which might be very labile, in particular of lipids and proteins. And the particles that we find in the water suspended in the summer, they carry a signal of recycling of organic matter. Remember this very strongly depleted C13 values. What is the fate of this matter? There is a very rapid burial of the eroded particles discharged in spring, and organic matter from aquatic production is apparently very rapidly degraded. With this, I would like to close, and I think I have already taken too much of your time, but I would not like to close without acknowledging all the contributions from very many colleagues whose names are listed here, and the list is probably not complete. And I would also like to acknowledge funding from some BMBF projects that we have been lucky to receive some support from. And I thank you very much for the opportunity of sharing those results, and I'm happy to take questions.
Great, great. This is fantastic, Gesine. This is a great talk. We know much better now about Lena. Of course, there's many unanswered questions. So that's very interesting. Let's see the audience now. If you have any questions, Liz, go ahead.
Hi, thanks, Gesine. That's just a really fabulous data set. I'm really excited about it. And I'm fascinated that you've got this, am I correct in understanding that you've got this ancient DOM coming out and it's not making it to the ocean? So what that means is it's going straight into the atmosphere? If I may just jump to the chase?
Yeah, well, this is what is suggested by the incubation data and also by our study in this island. So we don't really see this being carried out into the ocean. I mean, and not even into the river, the big river streams. Of course, there is dilution of quite a bit of material that comes from other sources, but it seems like all the old stuff that is thawed through these thermokarst lakes and escapes into the water bodies there, then also escapes into the atmosphere very rapidly.
Can you just speculate, following on from what you've just said, can you just speculate for me, what are the other sources? Is there, I think you said at the very beginning of the talk, they're very productive. So is there a lot of phytoplankton growth in the spring there?
Well, in the DOC C13, we don't see a signature of phytoplankton growth.
That's right.
So the DOC carries a C13 signature that is indicative of very strong predominance of terrestrial sources. And as we see a very high concentration of DOC in the spring freshet, this suggests that this mainly originates from the surface, from near surface sources. So when you have runoff from the surface of those soils that are really rich in organic matter, this is all dissolved in melting snow and in the groundwater that circulates through this very thin top layer of the permafrost, and that brings in a lot of DOC, also colored DOC that has been studied by Rafa, who's also here in the audience, out in the lab to see. So CDOM stuff, which I didn't include here at all because it's just too much. Yeah, but this is probably where it's from. Yeah,
great. I'm going to have to run, but thanks so much. I'm going to follow up with you later. Nice to see you. Bye-bye.
Nice to see you. Bye-bye.
Okay, anybody else? Oh. So Gesine, when other people try to keep up some questions, I do have a couple questions. This is so fascinating. So you said the organic carbon, after they transport to the shelf, and they degraded very fast, rapidly. And so do you have a little bit comparison to those tropical deltas or river system like Amazon? There's many studies like Bob Eller, even the Mississippi River or the Mekong. So how is there same speed, a little bit slow, or even faster? I mean, what's the maximum driving that?
I think the major difference in the terrestrial material that is transported by these Arctic rivers versus the tropical rivers is their history on land. Because if you put something into a frozen soil, it is largely preserved as it is. It's the pizza that you put into your freezer.
Sure. I see.
If you leave this out in the tropics,
they already burned.
Things growing on it, and it becomes moldy very rapidly, and it will be very strongly altered on land. So when you dump this into water, the previously frozen stuff is very highly bioavailable. In particular, the Pleistocene materials that are very organic rich and silty and really a yummy substrate for bacteria. So
this definitely makes perfect sense now.
Yeah.
I mean, in this sense.
Oh, I see. Look at it. Yeah. Sorry.
Is some of your colleagues also do the DIC, try to see the burning rate in the river water?
We have very few preliminary DIC radiocarbon data for this river, and it carries this recycling signature. So it is older than you would expect if there was a direct contact with the atmosphere. And it supports the suggestion that these rivers are sources of CO2. If you have older signature in the river, we don't have DIC concentration measurements. And this is really a pity. And I can, well, tell you why this is. Because sampling in these regions is one thing, and transporting those samples back to the lab is another. And if you sample for DIC, you have to keep it in an unfrozen state.
Yeah, yes, that's true.
And this is very difficult to maintain if you live in a permafrost area. It's very easy to freeze a sample because you just dig a hole into the ground and you store your sample there, and then it keeps frozen. But if you want to keep something at above freezing, it's not that straightforward. And this is why we lost many of our DIC samples, because they were frozen. And then the vials broke and we couldn't measure any DIC contents anymore.
The reason, because recently a colleague and I, we discussed a proposal, try to hook up on-field, on-site pumping system to measure the UCO2, the PCO2. And if we can hook up that, use a small boat, drive on, all the way from the river to the sea, then we can get a very good sense how much of the,
Yes, that would be very nice. Yeah.
Okay, well, we'll keep in touch. Okay, that's could be a good, because many people talk about those, ice river. They call it ice river. How much the CO2 release? Let's see other audience. Anybody? Limi, you have a question?
Yeah, I have a question.
Go ahead, Limi.
Good evening and good afternoon, Lena. I'm very glad to meet you again on screen. As we have, I have met you before almost 5 years ago in Bramley at your office. Maybe you already forget me, but
I do.
I'm very glad to meet you again. And also at that time, I received some guidance from your colleague at Jens, giving me some guide in the lab work at AVI. Today, I'm very interested to your very fantastic work about the Lena River organic carbon from the source to the sink. I'm very interested to the POC variation, especially I found that you find a very good result about the different C13 value between summer and between spring and summer and autumn. Recently, actually, we also do some POC work on the Lena River Delta and also the shelf of the Lactive Sea. We also find some interesting result about the C13 about the POC. For example, not only as you mentioned in the river channel, we also mentioned we also find some very negative POC values, C13 values on the shelf, but not on the delta, but on the shelf have a few distance to the river mouth. I'm not sure.
Sorry, can I ask? Is that suspended material or is it sediments?
Suspended particulate. We found also some very negative C13 values on the shelf about the suspended particulate matter. But as you mentioned, this aquatic organic matter from the summer or autumn will be degraded very rapidly. So I'm not sure how to explain this very negative C13 values on the shelf, because our field our investigation is also at the autumn, about the September at 2018.
I don't have an explanation right away like that, but I would think that there is always a pretty pronounced freshwater lens on top of the water column. And if you sample a lot near the surface in the shallow Laptev Sea, you might still get quite fresh water, which will contain also substantial amounts of terrestrial DOC and also recycled terrestrial organic matter. And once you go into this recycling bit, you will feed your phytoplankton or whoever lives there with DIC that is depleted in C13. So you get those very negative values. So that would be my best bet, that you have a relatively low. Did you get salinity?
Yes, we have the salinity. The salinity is about between 15 to 20.
Yeah, so it's still quite low, and you have quite a bit of terrestrial influence there, freshwater influence.
Yeah.
So sorry, 1 minute. I have to open the door for my son who's getting back from school.
Yeah. Okay. No problem.
Very nice talk.
Yeah, I'm fine. Thank you, Paul. It's very nice talk about the Arctic River, and as you know, I recently also very interested about the Arctic organic carbon work.
If possible, you're welcome to prepare a talk. We invite you to give a talk about your work.
Yeah, Arctic. Yeah, thank you.
Yeah.
Okay.
I'm back. Sorry.
Yes, I also think as you mentioned, the DIC process is also very important for the negative C13 value about the POC. I have another question about the POC C13 value. As you mentioned, we found some difference between the spring and autumn. Do you consider some influence about the black carbon during the different season? As we know, the in the summer or spring, the wildfire is very significant in the watershed about the Lena. So is there some influence about this burning carbon input at the later summer or autumn to do some different? Yeah.
So the question is, what's burning there? And if it's trees that are burning, they would all the black carbon particles would carry a signature that's radiocarbon young and C13 normal terrestrial values. So I think this is the main part that's probably burning. It's not so much the peats that produce black carbon, but that's a matter of investigation. I have never sampled any of those soot particles from the wildfires there. I would expect that to be a more important input during the summer season, when you have the hottest temperatures and less erosion per se. So the total load of particles that's carried by the river is smaller in the summer. And then if you have input from wildfires, you would potentially see them. I wouldn't expect that to be visible in the spring.
Yeah, thank you. I think the difference is very significant between different seasons. I will follow the result about your work. Thank you again. Thank you.
It's great. If you know any other question, I think we can stop here. So Gesine, thank you so much. I think that's wonderful. If Gesine, could you do me a favor? If you know any Russia colleague working on the Ober, Yeltsin, Lena, or Kalema sediment, organic or whatever, so please invite them to give a talk. I try very hard to try to get some Russian colleague, but so far I haven't successful yet. And if possible, extend the invitation to them. So hopefully, they can come here also give a talk.
I will. I can think of 2 colleagues, and I can.
That's wonderful, because so far, in this talk series, we have many colleagues from China, from Japan, Australia, Europe, but there's no still zero from Russia.
Yeah. Okay. I can think of something. Yeah.
Wonderful. Thank you very much.
Thank you for giving me the opportunity, and
Of course.
Have a good day.
You too. Bye-bye.
Or a good afternoon.